Okay, good. So I will start. Okay, I'll try and see whether it works. Oh, where's the mouse? Oh, that's why it will be. Right? It's a bit difficult to use.
Is a regular pointer?
I think it's fine.
We have a regular pointer.
I think Rogero cannot see,
Yeah,
right?
Okay.
Yeah, but I think it's fine. Yeah.
It's up to you.
Okay, so so our current understanding, so we know that the standard model and the lambda CDM cosmology works very well. But then there are a few open questions, which is experimental, because from observations we know that neutrino has non-zero mass, while standard model predict it to be exactly 0. And then we have more matter than antimatter asymmetry. So we will review that the standard model and the cosmology cannot explain what we observe. And then we have the cold dark matter in the CDM. So we have one of the components, we have no idea what it is. And then, of course, the lambda, the dark energy. So these are main open questions from the experimental point of view, right? And then if we, yes.
Is there hot dark matter evidence for that?
For example, a
So
neutrino
why
is a hot dark matter. Because most of the components will believe they are non-relativistic. But there are components, for example, our neutrinos, they are part of the hot dark matter, but it's a small fractions.
But
so
neutrinos are not dark matter.
They can be considered part of the dark matter if you want, yeah. It's small fractions. But then the majority, we know about 20% of the material, which is in the form of cold dark matter, which are important for structure formations and so on. Yeah. So this is like the standard. Of course, we have no idea what it is, so we just know they have to be.
The question is,
yeah.
why don't you call it just dark matter?
Because it is consistent with observation that is non-relativistic. Yeah. So we just call it cold. So if we treat the standard model as an effective field theory, we have the standard model Lagrangian, and then we can add a higher dimensional operators. And in this sense, all the heavy degree of freedoms, we are assuming they are heavy, so they are captured in terms of this higher dimension operator, the scale. And since we have explored up to around TeV in the Large Hadron Collider, so that means that we haven't been able to probe this heavy degree of freedom, which is hidden in this scale. But then we can construct a whole tower of higher dimension operator using the degree of freedom we have in the standard model. These are the standard model fermions, quarks, and the leptons. And then it turns out that, so this is an idea, first I think by Weinberg. And then this is so-called the Weinberg operator. So at dimension 5, we have only one. It's unique with 2 leptons and 2 Higgs fields. And then dimension 6, we have a lot more. But then there are only 4 of them which violate baryon and lepton number. So this will give rise to, in principle, proton decay. So in order to suppress proton decay, this scale has to be quite high. In fact, it's close to about grand unified scale, this lambda, which breaks baryon and lepton number. So if you look at the charges, this operator, the dimension 6, these 4 of them, which break baryon and lepton number, but they conserve a linear combination, which is different between baryon and lepton number. And then the dimension 5, they break lepton and B minus L, but they conserve baryon number. And then for the standard model, of course, it's well known that these are the accidental B and L, and of course the linear combinations. But then, okay, then we know that this gives rise to the tiny Majorana mass for neutrinos if after electroweak symmetry breaking. So this is very nice because it fits what we observe. Neutrinos are very light in this EFT picture. And then there's one important point is baryon and lepton number in the standard model is a symmetry of the Lagrangian, but at quantum level is not conserved. So it turns out that curiously, this B minus L is still exact. At the quantum level, it's still exact symmetry. Right? So these are what we understand.
So are you assuming these
Yes.
C's? I'm just curious why you have parameters C1, C2, C3, C4, and then you have another parameter in front. Are you assuming C1, C2, C3, and C4 are all of the same order, or what?
Yeah, I just put some dimensionless constant. So in principle, it can be of order of 1. But since they have different operators, so they have different constant. So it's some order of 1 number. So depending on your theory.
What's the argument? Why should they all be of the same order?
I understand you are saying about the, you're saying about this lambda scale.
Yeah. Why should they all scale the same?
Actually, it's just a parameterization. If this lambda scale is much smaller, that means the C is actually it's a combination. The whole is C1 divided by this scale. So I just separate, because in principle you have some dimensionless, the illusion coefficient plus the scale, no? So I just separate out. So this C2 can be, for example, very small, and then this scale also.
So nothing is known about C1, C2.
No, yeah, we know nothing.
It could be 0, it could be 100, it could be a million.
Yeah.
Nobody cares. Okay.
It's just that I split in this way just to, yeah.
I understand.
Yeah.
Thank you.
How many years does it take to know C1, C2, C3, C50,
How do we know?
How many years we have to wait to know about these numbers?
Well, yeah, it depends, I think, on both. If this scale, because I split in this way, so you can think of this as the mass of the degree of freedom that you can reach in the experiment. Yeah.
With the current experimental LHC that we have, can it prove that?
I don't think we can go very far above TeV scale. I mean,
We have to wait, say, 30 years?
I don't think, to probe this directly, I don't think there's any hope for the dimension 5 operator. So you can imagine if C is really small, and then lambda can be very small, even close to TeV or below. So people have thought about this kind of model. So you might be able to produce directly this degree of freedom if C is very small. Yeah. If C is of order of 1, then to get the correct neutrino mass, this lambda b minus L breaking scale is 10 to the 14 GeV. So of course you cannot reach. So it depends on the C. No? So these are model-dependent questions. Yeah.
How do you violate B and L in the standard model?
This is basically if you calculate the anomaly for this U1, this global symmetry. So then from the one loop, this triangle diagram with the SU2 current. So then it turns out this U1, you have a U1B and a 2 SU2 current. So this U1B, the global charge is not conserved. But then the thing is, this violation at today's temperature, we cannot see because it's kind of through the tunneling. Yeah, this is a paper by...
You're talking about instantonic effects.
Yeah.
Okay.
So it's very suppressed today. But just that this is important actually in the early universe, then you'll see some later, this will be important in the early universe.
Sorry, this B and L violation in the standard model are non-perturbative effects.
Exactly, it's a non-perturbative effects. Yes.
So you cannot write as a triangle diagram. It's more complicated than that.
You can represent it as a effective vertex, a tooth vertex, no, with a fuse, no. Like
with many particles, not only 3.
Sorry?
With many particles in the vertex. It's like a spalaron process.
Exactly, yeah.
So it's not a triangle. And the other observation is that you can probe this dimension 6 terms from proton decay.
Yes, if you, let's say you detect a proton decay, which is matched one of the operators, I don't know, one of them, and then meaning that you probe a combination of C3 divided by this scale, right? So you still won't know what is C3, and you would not know the scale, but you know the combination. No? So But I'm not sure the question is basically you can probe what is responsible for this operator directly. If that's so, then you have to reach at least this energy that you have to reach. Otherwise,
yeah, I meant you can put bounds.
Sorry?
I meant that you can put bounds on these operators from proton decay, or a combination of them.
Right, that's true. Because the current bound, if you put all the C1, C2, C3, C4 to be order of 1, then lambda BL is about 10 to the 16, 10 to the, yeah, close to the grand unified scale, 10 to the 16 GeV. So there are bounds, yeah. Yep, that's true, yeah, thanks. And so then from the cosmological side, so we have a brief history. So what we believe, well, now there's a period of inflation. And then after that, then we know, at least there's a direct evidence, there's the so-called fusion of proton and neutrons to form light elements. So this so-called Big Bang nucleosynthesis happens when the thermal bath temperature is about MeV scale. And then from here, we actually we can measure from the observed deuterium abundance and then the lithium-7, which is not very precise, and there's some tension. But basically from the deuterium and the helium-4, so we know that what is the number density of baryon in comparison with the photon density. So which is a very small number, but it's big enough that we are all here. And then from the CMB, we can also from the CMB fluctuation in the temperature, so we can also know how much baryon we have in the fluid itself. So and then these two numbers actually, these two very different period during the EV scale when the CMB photon is formed. And they give a number which is in agreement, up to a % level. So this is up to about 10%, let's say these two. So I would say it's a very successful picture. And so, but this number points to the need of explaining, because this is basically what they are probing is basically baryon, not the anti-baryon. There's no evidence. And then we have no evidence of a large quantity of anti-baryons from the observation. Because if there exists in the universe, then we should see at the interface of baryons and anti-baryons, you should see gamma rays, the source of gamma ray. Or even I think the strongest constraint comes from the distortion of the CMB spectrum. We don't see this kind of distortion from the annihilation and the baryon and anti-baryon. So what the evidence point to, we have this amount of baryon in comparison to photons, but no significant amount of anti-baryons. So this means we need to, so if we extrapolate up to much higher than GeV, that means the thermal bath has enough energy to produce a pair of baryon and anti-baryons. You have a lot of them. So that means that at the high temperature, you can translate this as an asymmetry. We have a bit more baryons than anti-baryons. So as the universe cools down, when it expands, then annihilation happens until in the end, you're only left with baryons. So these numbers have to match. So basically to explain this number, which is not huge asymmetry, looks like, but it's not that easy, depending on who you ask. So this mechanism to explain this number is called baryogenesis. And then it should happen after this period of inflations, so that you don't dilute this asymmetry. So and then the ingredients for this baryogenesis, the topic of the talk, is basically the so-called Sakharov conditions. And then there are three. The first one is we need baryon number violations. So this is the non-perturbative effect, which violates B minus B and L. So it can be captured by this, actually have involved 12 quarks. So this is the product of Q and L for 3 family, so it's a 12 quarks. But this process is at low temperature is exponentially suppressed by the inverse of the exponential minus of the inverse of the gauge coupling. So it's consistent because we don't see these kind of violations. But then, as pointed out, I think first by this paper by Kuzmin, Rubakov, and Shaposhnikov, that they are in fact efficient at high temperature. When actually it's before the electroweak symmetry breaking, because then this you go through thermal effects. It's not the tunneling from one vacuum to the other. And then the more precise number is this is a lattice paper, so they get more precise calculations that if the thermal bath temperature is above this, and then this process is completely unsuppressed, so it is proportional to the temperature itself. The rate, I mean the rate. So then the second, so the first one is obvious because you know that you need, if you want from 0 baryon number, you want to have access, you need to violate. And then the second is a so-called C and CP violation. So this, we know that the weak force only couple to left-handed fermions, so it violates C. And then there's a small CP violations because in the quark sector, so there's one non-zero phase. So that means the quarks and anti-quarks, they do not behave exactly the same. And then what turns out that this is kind of suppressed if you want to use for baryogenesis purposes, then because the whole CP actually is not just the phase, but it's proportional to the difference of the quark masses within the same generations. Since we have a very light quarks, like up, down, and they are very light. So if you combine together the CP relations, and then you want to apply it at above this temperature, around T above this temperature, so that you can use the source of baryon number violations, then this is too suppressed. The numbers just won't come out. So it is many order, like 10 order of magnitude smaller from what you need. And then the last one is the so-called out of equilibrium. So in equilibrium, from thermodynamics, you know that the baryon and anti-baryon, you have the thermal distributions. And then since you have a baryon number violation, so the chemical potential for baryon number is 0. That means the same distribution, then the same mass because of CPT, then you have exactly the same number density between baryons and anti-baryons. So to have out of equilibrium conditions, there are two possibilities. The first is so-called electroweak phase transitions. So this is possible because we know that from the electroweak symmetry phase, then now we are living in an electroweak broken phase now, because electroweak symmetry is broken by Higgs wave. And then the second is there because we know that the universe is expanding. So if we have some interactions rate which is a bit slower than the expansion rate, then it's not in equilibrium anymore. So we have a time scale which is the expansion rate of the universe. So the first one is well known that it doesn't work. This has been known since quite early when the Higgs bound is beyond this. But now we know the Higgs is 125 GeV. So in order to have strong first order electroweak phase transition, the Higgs has to be quite light. And then there has been many efforts to change the Higgs potential by introducing new Higgs or new degree of freedoms for this kind of purposes. But the second one is to make use of the ingredient, which is already there, which is the cosmic expansion.
Sorry, it's not my field. So I understand baryon number violation because you want different number of baryons and antibaryons, but why C and CP violation? Why do you need that? I missed that point.
Right. Because a simple example, because if you have a particle X, you can decay to baryons. The other one, it can decay to anti-baryons. This process violates baryon number. But then if the rate is exactly the same, because you need to differentiate between particles and antiparticles between the rate, then you won't get the excess. So
I see. So you need both 1 and 2 in order to have the baryon number violation.
yeah, you need to, in the process of generating baryon symmetry, you need to differentiate between particles and antiparticles. Otherwise, you you treat them the same, so you won't get the
But
access.
the first process stops when T goes below 132 GeV.
Right.
So why do you need out of thermal equilibrium? It sounds like it's frozen. So why do you need?
Why do we need out of equilibrium?
So if the temperature, suppose the temperature is below 132 GeV.
Right.
Then the number of baryons minus antibaryons is fixed.
Right, it's fixed.
So what's the condition about out of thermal equilibrium? I don't understand.
Right. The out of equilibrium, usually you want, for example, what you are mentioning is if you are exactly at this interface, around T equal 132, that means you are going into a baryon number in equilibrium to baryon number violating process out of equilibrium. Yeah. So this is the place that you can actually make use of this out of equilibrium. If you can generate a baryon number during this period,
okay, I think I understand. Okay,
then you can, yeah.
Okay.
Yes.
How does the third condition changes if the Higgs factor is more complex than only one Higgs? If there are extra Higgses, what happens? Is it still true that a strong first-order electroweak phase transition is impossible?
Yeah, it is possible. Yeah, this is basically the standard model, one Higgs conclusion, so it's possible. So yeah, so it's possible. I think the simplest model is to add a singlet Higgs, not the doublet, a singlet to the. You can have this. I think usually my impression, the more difficult problem after you achieve this, then you need how do you introduce a sufficiency violation? This is also the big issue. So I mean the conclusion in this talk is a new source of CP violation, and we'll make use of some interactions which is comparable to the cosmic expansion. So they are not in equilibrium. So this is just what kind of a summary, I'll say, for the B, L, and B minus L violation in the EFT. So if you look at the higher dimension operator, which is related to Majorana mass, meaning that we violate the lepton number by 2 units, but a conserved baryon number. And then this has been shown. Is proof if you construct the higher dimension operator only with the standard model fields, not the new fields. You believe that these are the only light degree of freedoms. And this operator can only be realized at odd dimensions, like 5, 7, 9, 11, and so on. So the first one, which is of the lowest order, is the dimension 5 that we have seen. So we are not sure neutrino is Majorana, but we know they have mass. So the first one is kind of half confirmed. If they are Majorana, then we should also see the neutrinoless double beta decay. That means a process of beta decay, but without emitting like 2 betas, but no neutrinos. So you violate lepton number by 2 units. So this has not yet been seen, but the experiment precision has been going down. So there's a hope that this is possible, that we see it. And then all dimension 6 and 8 operators conserve B minus L. So people have construct all the possible operators and confirm this. And then, but this although they conserve B minus L, but then you can have B and L can be violated by 1 unit. So this is what these 4 operators that we have seen at dimension 6. So they lead to proton decays. Of course, this has not yet been seen. Otherwise, you have known. This should be the biggest news, or one of the biggest news in physics. And then there's another interesting process. If the baryon number is violated by 2 units, but the lepton number is conserved. So this is also proof in this paper. It can only happen for odd dimension operators with dimension 9 or higher. So in principle, it's very suppressed.
Are there any even dimensional operators which violate B minus L that you know of?
Even number operator which violate B minus L.
Yeah, you argued D equals 4, D equals 6, and D equals 8 conserve B minus L. I'm just curious. D equals 10, does that conserve B minus L? People don't
B
know.
equal 10, let me think. You mean violate B minus L, right?
Well, you want 6 and 8 conserve B minus L, but you didn't say all even dimensional operators. Is there a reason?
Right, the
you said that?
7, dimension 7.
No, but 7's not even. What about 10 dimensional operators? Do they conserve B minus L?
Let me think. I think, because the proof, I'm trying to remember this paper. I think the 10, yeah, I'm not sure here.
Okay, thanks.
My naive thinking is yes, but I'm not sure. Yeah. Because I don't think anyone had construct all the operator, but this proof, at least from the proof, I don't remember that's the conclusion. So, yeah. And so just to stress that, at least for the dimension 5, 9, actually 7 also violates B minus L. Yeah, I did not put it here. Because 7 actually you can violate B minus L because you can have this kind of operator, like which is related to neutrino mass. But you can also have an operator which break L by 1 unit and B by minus 1 unit. So you still break B minus L. So this can also lead to proton decay, but it's just a distinct kind of other kind of signature. No?
In dimension 10, you have the dimension 5 square. That one violates, but B minus L. The dimension 5 square is just
right.
That violates B minus L and is dimension 10.
Yeah, this is an example, but in general, I don't know. Yeah. Yes. So now the idea is when you put these kind of global symmetries, no, or in general, or in the expanding universe. So then you have to think about you have a new time scale, no. So if the process is much smaller than the expansion rate, then you can have a conserved quantity, no, even though that process breaks your charges, no. So that means what you have to worry about now is also compared to the expansion rate because there's a new time scale. So this is an example for the standard model. So the exact is, there are a few reasons. For example, it's a gauge symmetry. No, this is U1Y hypercharge. It's a gauge symmetry above electroweak symmetry breaking scale. So it's exact. But then you have this B minus L that I told you. It's just because in the standard model, it just turns out to be exact. So it's a global, but it's exact. And then it turns out there's a 3 linear combination. I mentioned B minus L. In fact, there's the 1B and 3 lepton numbers. So then you can form 3 linear combinations which are conserved. And then after, electroweak symmetry breaking, you have the electromagnetism, which is conserved. But then you can have a lot of so-called effective. They are not there in the theory. For example, this notation means the right-handed top number. No? This is violated by the top Yukawa coupling, no? Because right-handed top can become Higgs, no? Through scattering and the left-handed quarks. But then if the temperature is so high that this scattering is not effective, because this scattering is proportional to T, but the expansion rate in the radiation-dominated universe is T squared. So if you go up in temperature, the expansion rate will be much higher, because it's T squared, than this kind of Yukawa interactions. The scattering rate goes as T. Well, there's no mass scale, no? Yeah, it's just Yukawa square and T. So that means that as you go down in temperature, depending on the strength of the Yukawa coupling, so more and more you get into equilibrium. No? The smallest one is completely out of equilibrium. Right? For example, you can have the right-handed electron number is completely conserved because this scattering through the electron Yukawa coupling is so slow, no, at the high temperature. So for example, if you generate asymmetry in the right-handed electron number, it will be conserved during this period because this number is conserved. So this is the idea of you have to think about this effective symmetry. And then here I mentioned the B. B is just, as you know, B is violated. It's also in some sense effective because we know that below this 130, 32, no, this temperature, this effectively baryon and lepton number is conserved again. Like we don't see them. But then if you go up in temperature, then this rate will be proportional to T when there's no Higgs barrier. No. But then again, here, B is conserved again. It's the same reason, because this rate goes as T, but the expansion rate goes as T squared. At some point, this violation will again go out of equilibrium. No. And so the idea, how do you generate a non-zero baryon number? So you try to introduce some new physics which slowly breaks one of the effective charges. So slowly just means that this breaking is not super fast, it's not super low, so it's relevant. So it's, at some point, it's about the same rate as the expansion rate of the universe. So then you still need, then you still need the second condition, which is C and CP relations. No? You need to differentiate between particles and antiparticles so that you can generate an excess. And then you can show that because baryon number is not a conserved quantity, so it should be proportional to some quasi-conserved charge. So when you generate this, break this U1 X, so it's not zero anymore, then at some point your generation or your genesis ends, then it becomes conserved again, no? So it cannot change anymore because this process stops, so it becomes conserved. Then the baryon number in general will be proportional to these charges, no? So this is the idea. So for example, if you introduce some model which violate B minus L, so in a out of equilibrium way, means in not super fast, no? And then you also have a new source or some source of CP relations, then that means that your baryon and lepton number will be proportional. So throughout this period, they will be proportional with some constant, which can be temperature dependent. But as you go below this threshold, then this will be fixed, no? Because the baryon and lepton number is conserved, no? So then it will be frozen, no? See, and the baryon and lepton number, finally you'll be frozen. So you can have a genesis which happens above. So these are the kind of the summary of how baryogenesis can work. So now I kind of go to the guts that I would like to discuss, the specific model. So there are a few hints which are well known. So the gauge coupling seems to kind of try to meet each other as you evolve up to high temperature. And then also one curious thing is in the standard model, if you sum up all the hypercharge of all the particles, they sum up to zero. Of course, this is also needed for the anomaly cancellations. But then it happens. So it's kind of mysterious. But then if you think about this, Y is actually part of some Lie group, no, SUN or SON. Then it's one of the generator, so which are traceless, then it makes sense that they sum up to zero. And then the third one, it has to do with, neutrino mass. Because neutrino mass are not there in the standard model, so let's see if a grand unified theory can make it. So for example, if you partially unify the matter, no, in the 5 and this 10 of the SU5, so you can fit all these I call 5 species, no, of the standard model particles in the 5 and 10. But then it turns out that since you unify leptons and quarks within the same multiplets, so that means the gauge boson which mediates the SU5 gauge interactions in general breaks B and L, right? But it turns out that there's a still accidental conserved B minus L is still there for this model. And neutrino is still massless because effectively there's no way you can introduce neutrino mass. Right.
So this first item there, this is a theoretical concept, right? There is no experimental indication that this can actually happen, or that there is some. This is some renormalization group argument, but
right. You use the standard model field content, so you just run the RG.
But there is no experimental indication that they actually
Experimental, I say no. I will just say experimental is just from what you measure at the low energy, then it just evolve up, then it's somehow it seems to.
So it's just a wild guess that eventually.
Yeah, just really just indications.
There might be non-perturbable.
Actually, I thought the SU5, just pure SU5, does not unify, given the measurements of the coupling constants of load scales. If you run the RG for pure SU5, they actually don't meet at one point in supersymmetry, if I remember correctly. Can you comment on that?
SU5, they don't meet. I don't really. In the standard model.
Yeah, that was his question.
Sorry, you mean standard model or SU5?
Rogerio, can you repeat the question?
The question is the following. If you take the standard model measurements of the coupling constants, coupling constants, and you assume that you have SU5,
okay,
and you run the RG renormalization group equations, the three couplings do not unify.
They do not unify, yeah.
You need supersymmetry for that. Can you comment on that?
Right. That's true. Yeah. Basically, that's you're just using basically standard model RG to run up, and then without supersymmetry, they don't meet. They kind of get close to each other, but they don't meet. But I think in the SU5, I think you can have because SU5 you have to introduce new Higgses, to break SU5. But then these new Higgses can affect the running of the RG. So if you take that into account, I think it's possible. It's possible even without SUSY. But I don't really have the article, but I think it's possible without SUSY if you introduce if you include this new Higgs in the RG.
Okay. Yeah. I also thought that minimal SU5 was excluded by proton decay. Is that correct?
I think it is correct. Yeah, the unification scale is it's too low. Yeah. But I'm not sure in SUSY, because I believe in SUSY is still okay, but without SUSY, I believe the unification scale is too low. Yeah. I think that's right.
Can I ask another question? Is the B minus L accidental conservation true for other models of grand unification, say SO10?
Yeah, in SO10, it's not accidental. SO10 is part of the generator of SO10. So now we have an explanation if we put this in SO10. It's not an accidental. It's a part of the gauge symmetry because it's part of the generator of SO10. So this is basically, okay, here I was just saying, okay, since B minus L is exact, so in principle, this also fails. People have looked at it in the past without, okay, it's not easy, but then once people realize it conserves B minus L, that means then you cannot generate a baryon number in this SU5.
Sorry, I just wanted to understand something.
Yes.
I think what Rogerio is coming, SU5 means that the constants is only one constant, right? If it's
yeah,
SU5.
Once they unify,
so of course they unify, but I think what Rogerio means is that it can't be SU5 because it doesn't correspond with the observation. Is that what you're saying, Rogerio?
Yeah.
It's not that they don't unify with SU5, it's that it's not consistent with the present values.
Yeah, I think if you just run up, because you use a standard model, RG, I probably draw it.
Yes.
But then you expect it to meet at some point. So this will be completely standard model running. So you say if here the unify is SU5 breaking scale. But then if they don't unify, meaning that, no.
That means it's not SU5. It doesn't mean that it doesn't unify.
But then in SU5, you actually have more Higgs content. No?
I see.
So you can actually affect the running. So you can it's possible from what I understand.
Okay. And this sum of hypercharge vanishing, is that required for some anomaly cancellation? Or
yeah, that's required for the standard model.
So I wouldn't say it's a hint of a gut. It's just...
Yeah, it's actually for consistency. But then still looks like, so for consistency of the standard model, but then it's still a curious point, about why this happened.
Okay.
Yeah,
thanks.
so, but yeah, it's true, it has to be there, yeah. And then if we look at SO10, then you can fit all the standard model. in the spinal representation, the 16. But then you need one more guy, has to be there. So this one more guy you can identify because it's not charged in the SU5 or the standard model gauge group. So that means it's a right-handed neutrinos. No? So I thought you predict 3 is because 16, these are all the one generation of all the fermions you can fit. So since you have 3 generations, so you are forced to have also 3 right-handed neutrino. And then now the B minus L is no longer mysterious because it's part of the generator of the SO10 in this. And then since you have to break SO10, you can have some intermediate symmetry, or gauge symmetry in between. Eventually, you reach the standard model before the final stage to the electromagnetism. So before that, you break, then effectively you generate this kind of operators, no? Dimension 5. You can generate this kind of operator, and so on. So in principle, this SO10 predicts Majorana neutrino mass, neutrinoless double beta decay, and proton decay, and so on. And then you can have possibility of baryogenesis because you break this operator as well. So that means your theory, you can have a way to generate non-zero B minus L and hence non-zero baryon number.
Sorry, I missed. You said it predicts, but can you say? You just say when you break it, somehow those terms can appear when you break it?
Yeah, those terms, you can actually calculate given if you specific breaking. So that means you kind of you can calculate this, no? Yeah, this has to do with the B minus L breaking scale, and then.
But I don't understand what sense it predicts it. So I mean, it comes from the breaking of the symmetry.
It comes from breaking SO10, yeah.
So in what sense does the SO10 predict something? Since it comes from the breaking of SO10.
Let me think.
No, but it's important semantics, right?
No, you know how these operators are generated. Let's say the source. It's not just you parameterize the standard model by a whole bunch of operators. So it comes from the SO10 breaking. So you actually have a theory to.
But can you say anything about the values of the coefficients?
Yeah, the coefficients that I think I will discuss an example. Yeah,
okay,
I think.
Thanks.
Yeah, yes. And okay, this is just a comment. Okay, so even in guts, you still have no idea of course the dark matter because there's no new particle which fits the bill. So of course, the more economical if you have black holes, which are some other thing. But since I won't be discussing, so I will just continue. So this is basically the outline. I think my talks. Okay, so basically, I will go through SO10 gut with the most important part is the Yukawa sectors because we want to generate the mass and mixing of the observed leptons, no? And then after that, I'll briefly mention how to calculate, the way to calculate the baryogenesis in this model. And then some predictions. No? After you do the fit, then what you get is, I call it something which you hasn't measured, I call it predictions. Okay. So just a quick summary that you have. Okay, the first one, baryon number violation, is already there. So, but then the new source of CP violation in the SO10 gut, these are just a few examples. So you have the singlets, the so-called right-handed neutrinos. So they can decay and violate B minus L. Then in principle, you also have the Higgs triplet, I think in one of the Higgs, which is needed to break SO10. So they have the triplets, Higgs triplet, which can decay into 2 leptons, which is also break B minus L. And then you can have other channel. This is a right-handed neutrino can decay into the charged lepton. This E is a standard model charged lepton, and another new scalar singly charged Higgs. No? So these are part of the you will see, it's part of the scalar field which you need. Then we can have out of equilibrium process. If this process occur at the rate which is not very fast, compared to the expansion rate at some point of the universe. No?
Sorry, when you say Higgs triplet, this triplet is respect to what age group?
Thanks for asking. This is a Higgs triplet under the SU2 left. Yeah, the SU2 left, the weak interactions. Yeah. Okay.
What is delta? What is delta in the previous slide?
Delta is a scalar which carry 1 unit of hypercharge. So it's and then it doesn't charge under the rest of the standard model. It just carry hypercharge.
Okay.
So, okay. So in the
sorry, one more question.
Yes.
One more question. The sources of CP violation have to put in by hand, right?
Yeah, it will come from the Yukawa couplings that we'll see next. It will come from the phases in the Yukawa coupling, yes, for this process. For the N, for the T, no, they have, so basically these slides, they come from this Yukawa coupling. These are the Y10, Y120, Y126. So these Yukawa couplings, they'll have complex phases in general, so they come from there.
I think it's just the fact that you have many more degrees of freedom and more phases that you cannot absorb, right? In the end, there's more free phases. Right?
Yeah, we can try to do rotation, and then you still end up with some phase. Yeah, so this is what we'll discuss here. So basically, if you put all the standard model plus 3 right-handed neutrinos. So you want to see how you get the Yukawa couplings. You want to couple 2 fermions to 1 Higgs, 1 scalar field. So then you do the direct product of the this group theory. So you see that you get 10. S is a symmetric product. This is an anti-symmetric product. So you can have a coupling to 2 possible Higgs with the conjugate. So that you get an invariant. So for example, you can couple to 10, 120, and 126. So these 2 are real, and then this is always complex, 126. So now the idea is how many Higgses do you need, no? Because I put this P just meaning that you can have many 10s, many 120, many 126. What are the minimum? So it has been explored very early on by Babu and Mohapatra that you need at least, 2. You need at least 2 to get a realistic masses and mixing. And then I believe actually the 2 cannot be just 2, 0, 0. You even need different types. Otherwise, cannot get realistic mixing and masses. So then you know that to get a seesaw, you actually always need 126. So this, otherwise you cannot get the seesaw mechanism to explain why neutrinos are light. So for example, the 126, if you decompose in terms of this SU5, so you have 1 singlet. So this singlet can get a wave, so you give rise to Majorana mass, in principle very heavy Majorana mass for the right-handed neutrino. And then you have the Higgs triplet that I mentioned, so in principle they are also heavy, so they will live here. And then the singly charged Higgs, or charged Higgs singlet that I mentioned, they also live in this 126. So in principle, this kind of process is possible if this guy is lighter than N. You can have this kind of decay. Otherwise, you have opposite. You decay to N and E. These are just one possibility that can be considered in this model, this process. And then,
sorry, where is the Higgs doublet of the standard model?
The Higgs doublet of the standard model is in the 5, for example, this 5. Yeah. So it's a 5, you can split into the triplet Higgs, which are heavy, then the doublet will be the standard model.
Okay.
Yeah. And then in general, it's a linear, it's a combination because we also need other Higgses. So it's not just this guy, it's combinations. So these are actually what is needed to actually allow us to fit to get the correct mass for the leptons. So basically, one of the so-called minimal model, you introduce 2 10s, or if you want 1 complex 10, and then 1 126. So if you do the calculation after you rotate, because this is symmetric, you can make it real and diagonal, and the rest you cannot rotate anymore. So you get 3 real and 12 complex parameters. And then usually people try to reduce, so they have to introduce an additional symmetry. This is just a U1, but it's called U1 Petré-Quinn. So you can reduce by 6 complex parameters. And it turns out that it works. No? Just that it's no longer just SO10, but SO10 cross Petré-Quinn. But then the other idea is if you insist not to introduce any additional symmetry, just SO10, then one which works is you put 1, 1, 1 in all of them. So here you still have in between actually what you have. You have 3 real, 9 complex parameters in your Yukawa sector. No? So it's kind of in between. So here, this is what we explore, no? The so-called minimal. So we can say maybe the second one is minimal, or yeah. So these are what we explore. And so to fit the mask, basically after you do all the group theory and so on, this is what you get, no, from the web of so basically these are all the, if you want the SU2 doublets, no, which is come from this higher dimension Higgs representation, no. So they have a different contributions, and then so then this is symmetric, and then this is a choice. You can make one of them real and diagonal, no. For example, this to be real and diagonal, or this. So we just choose the second one, the real and diagonal. And then yeah, then basically, then remember that the Higgs itself also can have a complex wave, no. So these are taken into account in this phase degree of freedom, no. So then this you come into the fit, no. So what I want to highlight is just how neutrino get mass. So basically, this is the so-called Dirac mass of the neutrino. This is the so-called Majorana mass of the right-handed neutrinos. So then if you diagonalize the matrix together with a light neutrino, a heavy neutrino, or I call heavy, left-handed and right-handed, then you get 3 light neutrino, which is mostly left-handed. No? So this can be represented by this diagram. This is the mass scale of the right-handed neutrino. And then you have the 2 Dirac mass. No? So it's a inverse. It's called the seesaw mechanism. And then this, you also have the type 2. Type 2 is basically, you can see it's directly this. This is a Yukawa coupling of 126 multiplied by the VL. So VL is actually an induced wave. So you can think of this picture. You have a triplets, heavy triplets coupled to the 2 Higgs. And then when the Higgs get wave, so the induced wave is basically the, okay, me means this coupling. This comes from a scalar potential between the Higgses. So wave square divided by mt square. So these are the VL. So these are so-called the type 2. So it's also realized in the SO10, naturally. You have both contributions. So for this analysis, we assume the type 1 seesaw dominance. So meaning that this contribution, because both of them contribute to neutrino mass, so we assume this is the dominant. Or you can interpret this as we assume this triplets wave, a triplet guy is very heavy, no, very heavy. So then you can get rid of this contribution in the analysis. This is the last term. So if you include the wave and the phases, so this is a total degree of freedom. You have 15 numbers, real number, and 12 number which appear as a phase. No? So usually phase are not considered a full number because in the fit, yeah, they cannot, yeah, it's more restrictive. No? So but if you compare to observable that we want to fit, you have 17 numbers and 2 phases. No? One is the CKM phase. The other one I call the PMNS is the CP phase in the neutrino sector. This has not yet been measured, but from global fit, you have some idea or some range that it should be, but there's no measurement. But still, so these are what we know. So if you compare, you can say that it looks kind of, I'm not sure, reasonable, but still you have 15 moduli, 17, so it's a bit less, but you have a lot more phases. But again, phases, you cannot treat it as a full number, no, in some sense. But still, you have enough degree of freedom to fit. So I call it prediction is something that has not, okay, it's not what we impose, no? That from what we observe, we impose the masses and so on. No? But then it's a Baryon number. We want to see whether we can get the correct number that we need, no? Correct sign and the correct order of magnitude. And then the n masses I call a prediction because these right-handed neutrino, we have not seen them. So we want to know if we know that their masses is like TeV, then it's possible to produce them and so on. And then the absolute mass scale of neutrino, we know the neutrino mass different. No? We know 2 mass differences between the 3 neutrinos, but we don't know what's the absolute scale. We know that have to be around 0.1 eV and below, but we are not sure where exactly it is. And then the 2 Majorana mass phases, which we haven't, because these can only be probed in the neutrinoless double beta decay, since we haven't seen them, so we cannot measure. So this will be the so-called predictions in this case. So just a quick summary of CP violation that we can have in SO10 for leptogenesis. So this is the decay of N to lepton and Higgs. So it's basically from the interference, because at the 3 level, there's no CP violation. If you calculate, the amplitude is exactly the same. There's no difference between the 2 decay rate. So if you include loop level, then it's possible you have a different. And then the important thing is these phases you come, besides the complex coupling, you also need to have intermediate state going on shell. So these are the kind of well-known that you need both of these in order to have CP violations. So this is basically what is proposed initially by Fukugita and Yanagida. But an interesting thing is that it's without grand unification. But at that point, they are thinking about SU5, and then you know that SU5 cannot work and so on. So they propose this simple idea. So it's not part of SO10. So it's just, there's a title.
So sorry, Sheng, I'm confused. You're saying that you don't have CP violation at 3 level?
At 3 level, you don't have CP violation because the amplitude is this one number, amplitude square. So it's exactly the same for the N decay to Higgs, the CP conjugate states. No? So at 3 level.
In the standard model, you do, right? In the standard model CKM matrix, you do have CP violation 3 level, no?
Do you? I thought you always I think you always need the loop, no? Even in the K mixing.
You need the penguin diagrams, right, Rogério? You need the penguin diagrams. You need a loop, right?
Yeah.
Then the loop will involve more than one CKM phase, and the total will not be 0. If you put just one phase, when you take the square, it goes away, right? So it needs to be a loop. It's the famous penguin diagrams, right?
Yeah, I was going to ask Sheng if you have a measure of CP violation, like the Yaroscourg determinant that you have in the standard model. Do you have something similar in this case?
Let me think. I think you can write in terms of some combination when you calculate these, for example, if you calculate these CP violations, then I think that it's possible, but I never really thought about this. It's possible to construct something like Yaroscourg invariance, which involve the Majorana mass and all the Yukawa couplings. Some combination. It's not just Yukawa coupling, but I think it's possible, but I never thought about this. Yeah.
Yeah, because otherwise it can be basis dependent.
Basis dependent.
Yeah, you can always make rotations, etc. No, and then things can be basis dependent. That's the whole point of the Yaroscourg invariant.
That's true. Yeah, here, that's a very good point because here usually the basis for the thing that we fix the basis is the mass basis of the N. N at the early universe, this is a basis that we always fix. But if you want to work in the basis that you can describe for even completely general, so I think you need that kind of formalism, yeah, to rewrite. Because here is just that because N have mass which is very large and very different from each other, assuming at the early universe, so you can really describe this is what is a state which is decaying from the kinematics and so on. So the thing is fixed is actually this is a mass basis of the decaying guy. But then the basis of the leptons doesn't have to be fixed. In fact, the formalism that I show, we can work in whatever basis. It doesn't have to align with the the charged lepton mass basis. But we fixed the basis of the decaying guy, yes.
Okay. Thanks.
And then, yeah, the second thing is just this triplet Higgs. Decay also have a CP relation because you can actually form the one-loop diagram with the help of the right-handed neutrino. So this is also what we are currently analyzing because we did not include this in the first paper. And then the other one that I mentioned briefly, this new channel is what we have include in our earlier work. This new channel. So they can have some effect. But since they are not directly related to neutrino mass, so it's not the effect. I mean, in our paper, it is of order of 1, so they do have some effects. Yes. Then the formalism that so it's already 1 hour now, so I will try to pick up the speed. Yeah. So if you have something else to do. So the density matrix formalism. So in this formalism is nice. So again, I stress that this formalism is only basis independent in the lepton, the standard model leptonic sector. So for example, you have in the standard model leptons. So this YE, the charged lepton, Yukawa, which give rise to the charged lepton mass, doesn't have to be diagonal. It can be arbitrary. So you can work in this basis. In the arbitrary basis in this mechanism, in this formalism. So the thing is you have to describe the so-called the charge density in the leptons, the left-handed leptons and right-handed leptons, in a matrix called the matrix of number density. So besides the diagonal part, which is just the number density in that basis, the actual number density, so you also have to include the correlation between different flavor. Or different index in whatever basis you choose. So in order to describe in a lepton flavor basis independent way, you need to describe in terms of this kind of matrix. So now the definition of this is just a difference between the leptons minus anti-leptons. I call it basically the asymmetry in the density. So then I just normalize by the entropy density. Because if the entropy is conserved in the co-moving volume, or in the early universe, this is very convenient, because if you multiply by some volume element at the bottom and the top, so then at the bottom, entropy is conserved in that volume. And then at the top, if there's no interaction in some volume that you pick, then the total number is conserved. So that means you are keeping track of actually the interactions which change the number of or create more leptons, anti-leptons, and so on. So this is a convenient quantity that is usually used if you are not familiar. And then in the standard model, if you include standard model, this kind of combination B minus L, this is conserved. So it's very useful to use. Because now if you include new physics, then that means that you can change this quantity. In the standard model, it won't change because it's conserved. If you start from 0, it's 0. If you start from something else, it's something else. So, and then this is include the standard model interactions. So then you have to describe it. This is basically the evolution of the 3×3. This Y is all 3×3 quantity, which are Hermitians. So they have the diagonal element, which are real, and off-diagonal, which are complex. And then, so then this is the Yukawa interaction. So basically, they scatter with the Higgs. So the Yukawa interactions. So you have to describe the one for the evolution of the left-handed leptons as well as right-handed leptons. So under flavor rotation, you can rotate with whatever basis you want. So the equation is covariance. Or it means that if you take the trace, since trace is this is a unitary matrix, the trace will not change. So that means what you can measure, for example, the Baryow number, which is the relation is the one I showed earlier. This number I get is basically you calculate when the Baryow number, this volating process get out of equilibrium at about 130 GeV. So these are the coefficients you get. Then this is just the B minus L. It's proportional to B minus L. So this depends on the basis. So when you include, for example, this type 1 seesaw or type 1 leptogenesis that from the decay of n, then you include the source term because the decay of n generate left hand change this B minus L in the left-handed sector. No? So you have to include the source term. This is just from the decay. Is proportional to this CP parameter, which parameterizes the difference between the decay rate to leptons and anti-leptons. And then the so-called washout rate, which is proportional. So this is all from the inverse scattering or inverse decay, because you can imagine if you create more anti-leptons than leptons, so then the inverse process will be faster, no? More anti-lepton to scatter back, no? So it tends to kind of bring you back to equilibrium, no? So this is a so-called washout process. And then you also have to evolve the number density of n itself, no? So this is basically is produced from the inverse decay, no? And then eventually you can start from 0, it still will be produced from the second term. So 1, this is basically the thermal bath is in equilibrium, so it's producing n. And then n itself can decay, no? So the decay rate is proportional to n. And then, yeah, this is just one complicated slide, but basically it's just a process that the quarks that we not mention, because quarks is there. So in principle, they are not the direct players. So for example, quarks can scatter with Higgs, no? You can induce asymmetry in the Higgses, and then the Higgs will scatter with the quarks. So the asymmetry, then you also induce in the asymmetry in the quark sector itself, no? So these are called the spectator effects. So it can be taken into account by the coefficients, which I show here, this CB. You know, CB is basically this is to take into account the fact that spharon, this process, no, I call it spharon, it breaks B only below 10 to the 12. No? So if you go above 10 to the 12, so this TB is basically about 10 to the 12 GeV. So if you go above that, then baryon number is conserved. No? So if you go below that, then it's violated. And yeah. So, and then finally, what we need to discuss is also the initial conditions. So after inflation, so this is the thermal bath temperature. After inflation, we believe the energy in the vacuum is converted to radiation. So what is the temperature in this radiation? So of course, we choose initially no asymmetry, because this is what we want to see, how much we can produce. And then how about abundance of N? We also need to have some guess. So since N is no longer a singlet in SO10, that means it will interact with the gut gauge boson. This is just an estimation. This is the SO10 breaking scale, this VR. So then this is a rate, T to the 5. So if you compare this rate and see whether this rate is fast, okay, usually we call it fast because we have to compare to something. We compare to the expansion rate of the universe. Then we see that this rate is indeed faster than the expansion. If the temperature is above this value, just a reference value, if you put this scale at 10 to the 14. Actually, this VR is a B minus L breaking scale because there's in the SO10, so you break SO10, then we break to some intermediate scale. So this is some intermediate scale, which is, we have the B minus L gauge symmetry, so we break it. So this, we'll see later, there's an intermediate scale. And then that means that there's an uncertainty because we have no idea what is the reheating temperature of the universe, so there's some dependence. So what we can do is we choose two reasonable possibility. If the reheating is much above, I think I put it opposite. If the reheating is above, actually N, you reach thermal equilibrium. So this initial condition will be thermalized N. So if the reheating is very low compared to equilibrium temperature, so then we can start with 0, assuming it's not produced. Then through inverse decay or inverse through scattering, then it's produced. So there's some dependence. So in our result, we include two possibilities. So they have to flip this. So basically, this is an analysis, which is just a chi-square fit. You taken into account this uncertainty. So basically after the fit, then we calculate what is the baryon number which is produced. So this is the observed number. So I change the unit, and then what we get is slightly bigger. But then the one in the bracket is if we assume the n is thermalized. No, so if it's thermalized, in general you can get some enhancement. Just in this case, there's some special effects that we discussed that it turns out to be the same. It's kind of coincident. But in general, if you assume more n, because if you have more n in thermalized n, then you can generate more asymmetry in principle. No? So the two fit, the difference is just we assume the neutrino mass is of normal ordering or inverse ordering. So for those who are not familiar, normal ordering meaning that the eigenstate which contain the most electron component, no, is the lightest one, and then the other one, the inverse ordering is eigenstate of neutrino which contain the least electron is the lightest one. So these are the two possibilities which are not yet determined. And then so the prediction, I call it prediction, is just these are the mass that come out from the fit, no, M1, M2, M3. And then this is some element, M beta beta, actually is some parameterization that people use to characterize the neutrino's double beta decay rate. So then the experimentalist can put bound on this quantity. So the experimental bound is in this range. So the range is big because there's uncertainty, I think mainly comes from the nuclear matrix element in their calculations. So that means, yeah, so what the fit give is smaller, so it's still consistent with the fact that we haven't observed, let's say. And then the other kind of predictions is the mass of the right-handed neutrino. So we have the heaviest one is very heavy. The intermediate one is 10 to the 12 GeV. The lightest one is about 10 TeV. So it's still too heavy to be produced. Besides the Yukawa is small, then the mass scale is very high. So, but this kind of spectrum gives rise to an interesting scenario for those who work in this field. So basically, you have mainly N2 genesis because it's too heavy. So basically, the asymmetry comes from decay of N2. But then N1 is there, so they can erase the asymmetry. No? So these are kind of combination. And then finally, a slight preference for normal ordering. This is just from the chi-square. It's not a big deal. And then we try to see whether there's some preference for the so-called delta 2-3, because in the neutrino sector, the mixing, the so-called theta 2-3 angle, we are not sure whether it's smaller or bigger than 45, you know, the first or second octane, usually people say. So from this case, we cannot have, because from the chi-square, we do not really have a strong preference for either case. Because in the green band is basically what we impose is basically the window of the global fit of the delta CP phase in the neutrino sector. So if you look there, you cannot say so much, maybe a slight preference for theta 2-3 smaller than 45. No. So, okay. And then the other one is gauge unifications. So we want to see whether they unify at the scale which is consistent with proton decay. So this is a gut scale. So from this channel, which violate B and L by 1 unit. So the super K, this experiment, they put a bound on the scale of gut, no? Meaning that you put the coefficient to 1, and then you kind of see what is the scale it has to be. So we try to, okay, so in this model, it's still possible to have a gut scale at quite high, but then you might question, it doesn't look to be unified, no? It looks like, the reason is just a threshold effect, because we actually play with the masses of the Higgses, no? So you can, in principle, they don't have to have same masses, no? So these are the threshold effects that is taken into account, no? To get this. So then, and then the intermediate scale that I mentioned is basically this SO10 breaks to the so-called Partisalam, the SU4 cross SU2 left cross SU2 right, the partisalam, with a Z2. So in the Z2, meaning that the gauge coupling of the left and right are the same. This is the intermediate group. And then after that, this scale is about 10 to the 14. So this is the scale, because B minus L is actually contained here as a linear combination. I think, yeah, linear combination of the diagonal generator. So that means that when you break this is a scale which you also effectively break B minus L. So you give rise to the masses of the right-handed neutrino at about, let's say, 10 to the 14. And then since depending on the Yukawa, that's why we have this very hierarchical spectrum. This just come out from the fit that the heaviest one is heavy, the lightest one is super light. And so then the SO10, okay, from here we kind of, from the fit at least, so we can say that it has to go through the 54H, the breaking, give rise to this partisalam with Z2. Because this is studied actually in the earlier paper. If they use 45 or 210, so they break to the intermediate symmetry without Z2. But the thing is the intermediate scale from the fit, it has to be quite low. No? So this is not consistent with the fit actually, not from the fit, but in this analysis, the intermediate scale, in order for unification to be consistent with proton decay, so the intermediate scale actually is quite low. But then this doesn't agree with the fit, no? Because the fit, we have neutrino mass, right-handed neutrino mass of 10 to the 14, no? The heaviest one. If the intermediate scale is so low, that means your Yukawa coupling should be super large, no? So it's not consistent with this picture. So more like, so this is just a slide that I steal from this paper about they analyze various ways that from the breaking of SO10, you can get the cosmic string if your intermediate gauge group has a U1. No? Then after you break the U1, you have some, non-removable loop. No? So and then from you can form this a string. No? In principle, the string can be infinitely long, but sometimes the string also can collide with each other and form loops and so on. So from this interaction, so you expect to get some stochastic gravitational wave according to this paper. So in this plot, so this is the gravitational wave which is obtained. So they consider two kinds of scenarios. So this is an inflationary scale after inflation. What is the inflationary scale? And then this is so-called cosmic string scale. Is when they break the intermediate gauge group which contain the U1. So this is when the string is formed. No? This is a string scale. So if you assume the inflationary scale is much above the formation of string, so the string is not diluted. No? So, but then the second possibility is when they consider inflationary scale is about the string formation scale. So string is kind of diluted. So that's why they get the signature which is a bit different. And then these 10 to the 15, 14, and so on is basically the scale where the string is formed. So in this case, since our picture is we break to this partisalam with a Z2, so we are following this part. So since we see that this is about, 10 to the 14, this intermediate scale, that means fitting into this picture, we should kind of fall into the regime where if string is produced, then we can probably have a sensitivity for the gravitational wave signature. So this is just a last slide, my remarks. So in this particular SO10 that we study, so these are kind of the conclusions that, I don't know why I have this, this is a bit shifted. Okay, these are just some conclusions. Probably I'll leave it at that. And then, the last part is just there are a few more works that study this gravitational wave from cosmic string. And then, this is actually my last slide. Just that, so God, for example, you do not explain why you have three families because you unified within per family, That's why there are still a lot of free parameters. So the idea is this can be reduce maybe further, it become more predictive if we impose some family symmetry. And the other thing that we are exploring is basically combination of type 1, type 2, and the other channels that's possible in SO10. Okay. Yep, thanks for your attention.
So what's the argument why you assume that you start with zero breaking after inflation? Is it just something that allows you to zero the clock, or is there an actual argument why it should be zero?
You mean the Baryon asymmetry is zero after the inflations?
Yeah.
If it's not zero, I think, it's more like a kind of, I don't know, you probably have to tune the asymmetry, the initial asymmetry before inflation. No? Or let's say after inflation, still you might have some leftover. In principle, it's possible. But then, usually in this kind of mechanism, I will call it, how they say, the strong, in the strong regime of leptogenesis, or in the sense that the interaction is fast enough. That means whatever you produce initially, let's say some non-zero number, in principle, they kind of erase it through this inverse decay, but then they are regenerate again. So in some sense, it's not very sensitive to the initial condition.
So you say it doesn't affect your predictions if it's not zero? Is that what you're saying?
It doesn't affect most of it depends, but at least from the fit, we are in the regime where, let me be more specific if I go back what I'm trying to say. Let me go back. I was trying to say.
So there you initially no matter antimatter.
That I put zero, but I was referring to this kind of this term, the so-called washout. So let's say initially you have some delta L, delta H, you have non-zero. But then this kind of washout is kind of effective. So usually at the high temperature, it actually erases whatever is there. Then at a low temperature, when the N is produced initially, N start to decay again, you regenerate. So it's very insensitive. But there are parameter space, at least not in the fit, there are parameter space that this interaction itself is really not so efficient, so you cannot erase everything else. Then it becomes non-predictive at all. That's a very good point.
Any other questions? Okay, let's thank Chee-Sheng.
Gravitational gravitational wave from cosmic string, but cosmic string